In this section of chapter 11, we'll like to discuss about homework problems on intermolecular forces and phase diagram. We are going to begin with problem number 7, page 454. So they gave you a phase diagram, and I have tried to draw this, but it was not drawn to a scale, so it's not going to be exactly the same as what you have in the book. But I'm going to write down a few numbers on the graph so that we can explain at least some of the answers. But in order to get more accurate answers, you'll have to go back to the book and try to use your ruler to get exact numbers. And I'll tell you how I get these approximate values. So in this phase diagram, let me first explain to you. On the left side you see solid, on the right side of that curve you have liquid, and on the far right you get gas. So let me show you different color. So okay, this is the curve for solid. I'm showing you in green. It goes like this. That's solid. On its left side you have solid, on the right side you have liquid. I'm talking about above this point. So on this side you have liquid, on the left side you have solid. Now that's true for this green curve. Now in this phase diagram, the red curve, on the right side, on this area, you have gas. On the left of that area, you have liquid. So basically you're seeing all these labels. So only in this, between this green line, this line, and this red curve, you have liquid. On the left of that line, you have solid, as well as this green curve, you get solid. And the right side, you have gas. Right side of both red curve as well as the solid bottom curve, you have gas. So now let's put down some of the numbers and then we'll go from there. So triple point where these solid, liquid, and gas curve they meet, it should be about 180 Kelvin. So let's put down 180, and rather than degrees centigrade, I think in the book these are all in Kelvin, so let's put down Kelvin. And 100 would be somewhere here, 100, and so you would have 200 close to here, and then 300 would be somewhere here. That's 300. And then, as I mentioned, that these are pretty approximate. 400 somewhere here. I just wanted to give you an idea how you can work on this kind of problem. And triple point pressure is about 0.4. So that's 0.4. And the unit is atmosphere. So the unit is ATM. Let's write down here ATM, atmosphere. So 1 would be somewhere here. That's 1.0 atmosphere. And 0.5 would be somewhere here. Okay. Now with this in mind, let's try to answer some of the questions. The question A. Normal boiling point. Normal boiling point means is the boiling temperature under 1 atmospheric pressure. So basically you draw a solid line horizontal to 1 atmospheric pressure. So let me draw that line in blue. So I'm trying to get it as horizontal as possible. So something like that. Okay. and then you get vertically downward, so you get somewhere in here, somewhere in here. So that's approximate, I would say, 350 Kelvin. 350 Kelvin. So that's an approximate. In order to be more accurate, as I said, you have to use ruler and go by, say, your 1 inch is 120, then half of an inch would be 60, so that's how you can get more accurate number. But this is pretty approximate that I'm showing you. Now, normal freezing point, again, this is the freezing temperature or melting temperature under 1 atmospheric pressure. This would come from the green curve, which goes from triple point upward. So I'm talking about the curve where, again, I'm going to show you a line with the blue line. So that's, I'm going to extend downward, and so it would go somewhere here. So let's make this number is around 250K. 50K. So normal freezing point would be 250K. Now in 7b, the question is, what is the physical state of the substance under following conditions? Temperature is 150K, so they're saying that temperature is 150. Pressure is 0.2 atmosphere. Okay, let's draw a line here. So you need to say what kind of physical state you would have. So temperature is 150K, so it'd be somewhere here. The temperature we're talking about along this line, in between 100 and 200, that'd be 150K. Again, this is not drawn to scale. So you get to 150K, and then 0.2 atmosphere is going to be somewhere here, 0.2. Let's write down 0.2. So that's 0.2. So it goes like this, and that's where your point is. And this is gas. So answer is, state of the matter is a gas. In the same way, you can answer the other questions. In part C, what is the triple point of the substance? So triple point is given by this point where three curves meet together. Solid liquid curve, which is the vertically that going upward. Then the curve, which is showing liquid gas equilibrium curve that gives boiling temperatures. And the bottom curve, that's giving solid gas equilibrium. That's sublimation curve. At any temperature below triple point, solid would be directly converted into gas. It never goes through a liquid. So make sure you do other parts of part B, and that's how you'd understand this better. Now we're going to discuss problem 17, A and B. Now the question is, describe the intermolecular forces that must be overcome to convert these substances from a liquid to a gas. So we need to identify what kind of intermolecular forces exist between these molecules like SO2. In order to do that, first you need to get Lewis structure, then you find out whether it's a polar molecule or a non-polar molecule, and then based on that you can identify what type of intermolecular forces exist. Now SO2, so you need to write down the valence electrons. Let's write down SO2 on the top. Sulfur is from group 6A, and those would have valence electron 6 or outermost electron 6. Or you can also count from beginning of line 2 until you get to oxygen, and you'd find oxygen is the 6th element in line 2, and that gives the outermost 6 electrons. So sulfur has 6 electrons. Oxygen is also from group 6A, so it would also have 6 electrons. Now we have 2 such oxygen, so 6 times 2, that's 12. And altogether we have 18 electrons, and we must account for 18 electrons in SO2. At this point, I don't know the shape of this molecule. I'm just going to write down Lewis structure. And so Lewis structure doesn't care about shape, so just write down any way you want. Let me write down like this, SO, because we know the central atom would be sulfur, present in least number, and outer atoms would be oxygen. Then you give noble gas configuration to the outer atoms, so make 8, 2, 4, 6 additional electrons, 2, 4, 6 on the oxygen. Now I have assigned 16 electrons altogether. Now I have 18 electrons, so 2 electrons will have to be on sulfur because oxygen already has noble gas configuration. So I'm putting down, I have already placed 2 additional electrons on sulfur. Now this is still not quite I'm not quite done with Lewis structure because sulfur has now altogether 6 electrons. It would like to have 8 electrons. But there is no other remaining electrons, valence electrons. So what we're going to do in this situation, bring in 1 electron pair from one of the oxygens, either from right or left. Let me use a different color, and bring it in between sulfur and oxygen. In other words, make a double bond between sulfur and oxygen. It can happen from either side, so it doesn't really matter. So now, and that would give you actually 2 resonance structures. Here we don't really worry about that, but let's just write down one of the resonance structures. I would have a double bond here, and then 2 pairs of electrons on oxygen, and 3 pairs of electrons on the other oxygen. This is exactly how you're going to do this problem. Now we need to know the shape, because whether it's going to be a polar molecule or not would depend upon what kind of shape it would have. If it's a linear, sulfur-oxygen interactions on both sides would completely balance it and make it non-polar molecule. So we don't know this linear or not. Let's first figure out that. How many electron domains you have? The double bond you have between sulfur and right hand side oxygen would count as 1 electron domain, and the left hand side one, this is the second electron domain. So these are the 2 electron domains. The third one is solely on sulfur, so there are 3 electron domains. So 3 electron domains. Remember, for 1 electron domain you have, for 2 electron domains you would have sp. 3 you'd have sp2 hybridization, and sp2 hybridization goes with 120-degree angle. Now let's write down this structure. So writing down linear structure with 180-degree angle is not right. So the right structure I'm going to write down now, right shape, would look like this. Even though you have a double bond on with 1 oxygen, the other one single bond. Now I'm not showing any more of those electron pairs because I'm going to show you what kind of molecule is this. So this is the bent molecule, and the angle is around 120 degree. Of course, this will be squeezed a little bit because of the unshared electron pair solely on sulfur. Now, let me now draw dipole forces. Sulfur, oxygen. Oxygen is more electronegative than sulfur, because if you look at periodic table, it's on the upper, right on the top of sulfur is oxygen, which is more electronegative than sulfur. So that means oxygen is pulling electron away from sulfur. So let's have a draw an arrow here. That's the dipole moment. And on the other side also there'll be another one. Now these forces are acting at an angle. So what that means is, as a result of these 2 forces, there is a net effect in between. I'm showing you with a green arrow. So there's a net force on it. If you consider sulfur to be a table and two people are pulling the table at an angle, the table is going to move, and that means there's a net force. And when there is a net dipole moment, it's going to be a polar molecule. So let me write down here, it's a polar molecule. Remember, for a polar molecule, we have dipole-dipole interaction, intermolecular forces. Let me write down all the intermolecular forces now. Dipole-dipole intermolecular forces. And another force, intermolecular force, exists in every molecule, which is due to a dispersion effect, which is called London dispersion forces. So London dispersion intermolecular forces. But the major one is dipole-dipole. London dispersion is present in every molecule, and this is we are going to always mention, but predominant one is dipole-dipole interaction. So we need to overcome primarily dipole-dipole interaction between SO2 molecules, and also there is this weaker interaction of London dispersion forces in order to convert these kind of substances from a liquid to a gas. Now let's now talk about CH3COOH. This is an organic compound, and I would save my time by not counting valence electrons. I know that carbon must have 4 bonds, and oxygen must have 2 bonds, and hydrogen can only have 1 bond. With that in mind, I can quickly write down the organic structure for this compound. So let's write down that. CH3, all these hydrogen, 3 hydrogens are bonded to carbon. Then you have C. First write down O, because we're not sure at this point how it's going to work out. OH. Carbon must have 4 bonds, but I have 3 bonds, so let's make it 4 by having a double bond. So that's COOH. Remember, each carbon now has 4 bonds, oxygen has 2 bonds, and of course you must have 2 pairs of electrons. 1 pair, 2 pair. Now let's try to get the shape, and in order to know whether it's a polar molecule or not. But before that, one is quite obvious. Hydrogen is bonded to oxygen, so you must expect hydrogen bonding. So let's write down here. One of the intermolecular forces here would be hydrogen bonding. I just want to remind you, hydrogen bonding is possible when hydrogen is bonded to oxygen, nitrogen, or fluorine. In other cases, there will be no such hydrogen bonding. In hydrogen bonding, hydrogen acts as a bridge in holding 2 molecules together. Okay, now let's find out whether the overall molecule is polar or not. Now for that, we need to draw the structure right around each center, especially which may contribute towards polarity. Oxygen, you have 4 pairs of electrons. 2 pairs are sitting solely on oxygen, and other 2 are bonding pairs. So that's sp3 hybridization. So that's sp3, and that goes with 109.5 degree, but close to 109 degree, because it's going to be squeezed because of those 2 unshared electron pairs on oxygen. And we don't know exactly the angle, but we can say it's a close to 109, but slightly smaller than 109. Now let's focus on next central atom, which is this carbon. Now there are 3 electron domains around that carbon. The one domain is due to the double bond. The other 2 are single bond. So 3 domains would be sp2 hybridization, and sp2 goes with 120 degree angle. Let's draw this structure and shape more accurately. That way you can answer this question. So you'd have, let me write down again in blue, C double bond O, then you have CH3. I don't need to worry about CH3 because carbon hydrogen is bond is almost non-polar, so it's not going to, polarity would not be contributed by uh, the CH3 group. So this is 120 degree, so I'm drawing it that way. This is 2, 4, and then I can write down hydrogen either upward or downward, doesn't matter. So hydrogen is going this way. Actually, we are running out of space, so let's have it. Okay, we need to figure it out like this. Okay, now you get an idea about what may contribute to dipole moment. Let me show you all the forces. Carbon, oxygen. Without looking at electronegativity table, I know that oxygen is more electronegative than carbon. So let's draw those forces. And so one force is going to be from carbon to oxygen. That's one of the forces. Other force would be also from carbon to oxygen. And these are the two net forces, and the net force is going to be in between. So if you just ignore other forces, so it's going to be this force. The red one is formed by combination of the two green forces, or green dipole moments, shown with green arrows. Now OH bond. Oxygen is more electronegative than hydrogen. So let me draw that arrow, and I'm going to use a different color now. I'm pretty much running out of the colors here. So let's draw that arrow, that from hydrogen towards oxygen. Now we have two net forces here. I already took into account the other two forces. Now this is the third one I'm looking at. Now basically you now need to look at net effect due to these two forces, the red and the yellow ones, and see that they're not equal and opposite. So they're not going to balance out. So there'll be net force somewhere, approximately, again this is not going to be that accurate, it'll be somewhere along this direction. So this is going to be a polar molecule. So hydrogen bonding is one kind of intermolecular force existing in this compound. In addition, you'd have dipole, 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 dipole. And as I said, London dispersion force is there because it's due to polarization effect. So dispersion force. So all these forces we need to overcome in order to convert these substances from liquid to a gas. Here we're going to begin with problem 17C. So 17C, they're asking for intermolecular forces that must be overcome to convert these substances from a liquid to a gas. So the substance is H2S. So before I figure out what kind of compound it's going to be, I must get Lewis structure, because whether it has a linear shape or a non-linear shape, that would make a difference whether it's going to be a polar compound or a non-polar compound. So sulfur is from group 6A, has 6 valence electrons. Each hydrogen has 1, and 2 of them would have 2 valence electrons, and altogether there are 8 valence electrons. Let's write down Lewis structure now. Again, we don't know at this point what kind of shape it's going to have, so let's write down whatever way you want. Let's assume this is a straight line or linear. This accounts for 4 electrons, and I need to assign 4 more electrons. Hydrogen already got the noble gas of configuration of helium with 2 electrons or 1 bond. So you cannot put any more electron on hydrogen. So those electron pairs will have to be on the central atom, sulfur. So this is the two pairs. And this would account for all 8 valence electrons in H2S. Now let's figure out the shape based on the number of electron pairs. I have 4 electron pairs, and that means hybridization is going to be sp3. Remember that you need to combine 4 orbitals because you need 1 hybrid orbital for each electron pair. So sp3 goes with 109.5 degree. So this cannot be a straight line or linear molecule. It has to be a bent molecule because to be linear, angle has to be 180 degree. So now you can write down here as SHH. This is not going to be quite 109.5 because 2 unshared electron pairs on sulfur is going to squeeze that angle to a smaller value than 109. So let's write down like this. And now we can answer this question about what kind of intermolecular forces are there. Now between hydrogen and sulfur, sulfur is more electronegative, and this would be like this. The other force would be like this. So net force would be in between. And so it's going to be a polar molecule. And obviously, you'd have a dipole-dipole intermolecular force. Let me write down here. Dipole-dipole. There is no hydrogen bonding here because hydrogen is not bonded to oxygen, fluorine, or nitrogen. So that's you can rule out, but there is a dipole-dipole interaction and also dispersion force, London dispersion force, which exists in every molecule, as I said, but all these types of intermolecular forces work together. So in this case, the major force to overcome would be dipole-dipole interaction, and then would be London dispersion force. Now let's now go over number 18A. Let me read you the question first. 18A. Which type of intermolecular force accounts for the following differences? They're saying that CH3OH boils at 65. So boiling point is 65 degrees centigrade. On the other hand, CH3SH boils at 6 degree. The boiling point is 6 degree centigrade. So in case of CH3SH, boiling point is significantly lower. Now why there's a difference? Let's look at the structure first. Now we need to draw the structure to understand this. Again, your methyl group, you have CH, H, H. Carbon must have 4 bonds, so oxygen, and oxygen must have 2 bonds and 2 pairs of electrons, OH. I'm assuming that at this point you know what kind of shape it would have. Is bent because oxygen have sp3 hybridization, angle would be 109.5, so you cannot draw it as a linear geometry around oxygen. So that's what you have for CH3OH. Now for CH3SH, I can write down like this. CHHH. And then instead of oxygen, I have sulfur. Again, it's the same kind of angle. Now here, make sure we realize that in this particular compound, hydrogen is bonded to an electronegative oxygen. So this can give hydrogen bonding. Whereas in case of second compound, there is no hydrogen bonding, no H bonding. But the other ones, like dipole-dipole interactions, they are present. London dispersion force, even though it's weak, is present. So the major difference is caused by hydrogen bonding in case of CH3OH and no hydrogen bonding in CH3SH. Here we're going to do problem 18b and 18c. The question is asking which type of intermolecular force accounts for each of these differences. So in part B, let me write down the B. Xenon is a liquid. So xenon, Xc, is a liquid. So that's liquid under 1 atmospheric pressure and 120 K temperature. On the other hand, argon is a gas under 1 atmospheric pressure and 120 Kelvin of temperature. So under the same experimental condition, xenon is a liquid, but argon is a gas. Why? Now, if you look at the location of argon and xenon in periodic table, you'd find that they are within the same group, which is 8A. As you go from argon downward, you get then krypton, xenon is the next to it. As you're going downward, size is getting bigger and bigger. So if you remember that this is how it goes on. As you're going downward, size gets bigger and bigger. So this way gets bigger in size. So xenon is bigger, a lot bigger than argon. So let me draw this. So xenon, if this represents size of xenon, is bigger. Argon is much smaller. Let's use a different color. Argon having bigger size and quite a few electrons there, and those electrons, especially the outer electrons, are much farther away from the central nucleus or positive charge, so they're less attracted to the nucleus. In other words, those electrons are quite polarizable. You can polarize that quite readily. So when a number of xenon come close to each other, let me show you what may happen so that you'd understand that why xenon is more polarizable. If these two xenons, say for example, are coming close together, so let's first assume that this is pretty much undistorted. Okay, as they come closer, electrons repel each other. So there'd be development of negative charge on one end, and it's going to polarize the other ones by pushing electron away from that end. So electron will be going away to the other end. So this end, the one that is close to the first xenon, is going to have positive charge. That's how there is an attractive force. And the farther end, it gets the negative because electron gets more concentrated on that end. So this kind of polarization makes xenon-xenon bonding stronger than argon-argon bonding. In argon-argon, electrons are not as loosely bonded. Electrons are not as loosely bonded as in case of xenon. So they're less polarizable. So what effect you're seeing on the top is not going to be exactly the same kind of effect for another argon. So because of greater polarizability, we can say that xenon atoms are held together more strongly. And since it's held together more strongly, xenon is a liquid. Whereas argon shows smaller amount of such London dispersion force, or dispersion effect is much smaller, and that's why They have a smaller interactive force, and that's why argon molecules can move a lot more freely and remain in gas phase. So completely based on London dispersion force, we can talk about interaction between xenon and argon. So keep this in mind. The larger noble gases are more polarizable than the smaller noble gases. Now we're going to do 18C. So now we're going to do 18C. Again, it's a similar problem. Account for the difference. In case of krypton, molecular weight is given 84. The boiling point is 120.9 Kelvin. In case of Cl2, molecular weight is slightly lighter, but about pretty close in in the weight, and the boiling point is much greater, 238 Kelvin. Answer is why. Why Cl2 has a much larger boiling point than krypton. Again, it's basically the same issue. Two atoms of Cl, it's a diatomic. If you consider the molecular whole molecule and having the electrons around it, it's much more polarizable. So 2Cl, when they Cl2 that's approach close to each other, you see a larger polarizing effect. So that means you'd have a negative end, positive end, negative end. That's how it works. So Cl2, a diatomic molecule, would show greater polarizability than krypton. Krypton is not as polarizable because it's just a single atom. So two atoms, like two Cl atoms, would be much bigger than a single krypton atom. So writing down like this, krypton on krypton. They're also polarizable, but not as polarizable as diatomic chlorine molecule. And for that reason, interaction between chlorine molecules would be stronger, and that's why you need to heat it to a higher temperature to break those bonds and to send liquid Cl2 to a vapor phase. In other words, boiling temperature is going to be higher for Cl2 than for krypton. Now we're going to discuss problem 18D. Again, the question is, which type of intermolecular force accounts for each of these differences? So they have given you acetone structure as well as 2-methyl propane. So let's first draw them before we think about this answer. So acetone, CH3, C double bond O, CH3, this is acetone. Then 2-methyl propane, CH3, C, CH3. Then obviously you have CH and CH3. So acetone boils at 56. Let me write down the boiling points that they have given you. 56 degrees centigrade for acetone. And 2-methyl propane, that's the right hand side compound, boils at minus 12 degrees centigrade. So basically that suggests that acetone has a much larger interactive forces. Now let's try to understand that. Why is that? In case of acetone, we have 3 electron domains. Double bond would be counted as a single electron domain, and there are 2 single bonds on 2 sides. So with 3 domains, you'd expect sp2 hybridization, and that goes with 120 degree angle. Let's draw it. So C, double bond O, CH3 on this end, CH3 on the other end, and the bonding is through carbon. And these are 120-degree angle. Now you can see that oxygen is more electronegative than carbon, so we can draw the dipole moment, the force that's pulling electron away from carbon. So overall, this is a polar molecule. Polar molecule. On the other hand, if you look at the other compound, 2-methyl propane, is a non-polar molecule. It's sp3 hybridization. If you draw actual structure, it will look like this. CH3, 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 and you would have hydrogen. Now carbon-hydrogen electronegativity difference is very small. Not only that, if you look at all these carbon-carbon, that's the same electronegativity, and carbon-hydrogen has slight electronegativity. So compared to the first compound, the polarity of this is very small. So we can say almost non-polar. So all practical purposes is going to be non-polar compound having a slight polarity, but this is significantly more polar compound is acetone, and that holds acetone molecules through dipole-dipole type of interactions. And because of these stronger intermolecular forces, acetone would have a much higher boiling temperature point than 2-methyl propane. Keep in mind, London dispersion forces are present in both cases, and that would be the weaker type of force.